Welcome back to ECE 441A, 541A. Homework number 8 has been posted, and it's due on the 1st of December, which I believe is maybe a Thursday. Different date, just keeping you alert. I have also given you additional material on sketching Bode plots if you want to sketch Bode plots. We had a new student that decided he was in the wrong class and left, but that's okay. We welcome all comers, but if you are interested in reviewing any of the Bode plot material, it's on Unit 8 supplemental material in that same unit. Lab number 3 is due the last day of class, which is the 7th of December, and projects, whoa, obviously it was late last night. It's already past due based on today. Deliverable number 1 is delinquent, but please submit that if you haven't yet done that. I think the box is still open. And our final exam is on a Tuesday, not a Monday, not a Wednesday, not a Friday. It's on a Tuesday. And it's at 10:30, so I guess you get to sleep a little later. Oh, you have an 8 a.m. final on that day also. Congratulations. So you'll be all warmed up for class. Here's just some material for reference purposes in terms of where you can find Bode plot material. Chapter 8 tells you how to sketch and analyze Bode plots, and the design piece, which we will talk about designing lag filters, phase lag and phase lead filters with the Bode plots, and that's in Chapter 10. You can also look at some representative Bode plots in the different tables, Table 2 in Chapter 8 and Table 3 in Chapter 9. I hope you all did your homework for today, which was to sketch that Bode plot that we left class with last time. Then we will have a quiz. Since it's the last day before a break, everybody, gives a quiz to make sure the attendance is here. So we'll stick with that theme, and that will be on stability margins. And then we want to do what I've been calling now this inverse Bode plot concept. It's basically identifying the system, finding your transfer function if somebody gives you the Bode plot. If somebody hands you the frequency response, magnitude and phase, can you now extract from that a transfer function G of S? So on the final, I could give you a Bode plot and say, control this system using a root locus technique. And it might really throw you, but now that you've attended today's class, it won't. And all of this is designed to hopefully help you navigate through homework number 8, which if we get through the system identification, that should be enough to give you the material you need to complete homework number 8. We'll then move into designing phase lag controllers, and so you can anticipate we're going to have more than 8 homework assignments this semester. And we will start with a phase lag controller since we were sort of focusing on phase lead with the root locus. Let's start with phase lag, and that's to allow us to reduce our steady state error. If you start doing lab number 3, you'll find that with the phase lead controller, you get a pretty big steady state error, and maybe you don't want that. You can eliminate it with a PID by putting an integrator in the system, but you can also reduce your steady state error by using a phase lag controller. But that actually has the result of probably slowing down your system, meaning it doesn't speed it up. A phase lead is typically going to speed up your system response. That's what it's designed to do. That was pulling your roots further into the left half plane. A phase lag is really saying, I'm not so worried about increasing the speed of my system, but I'm more worried about the steady state accuracy. And that's what a phase lag is designed to do. This was your example for homework, and we wanted to sketch this particular transfer function. It's right now written in pole zero form, and can you now put it into time constant form? Or have you already done that? Show of hands, how many completed their homework assignment? Turn it in. I'll give you your time to write your name on it. No. So is it clear how you would convert this into time constant form? Time constant form is what we want our transfer functions in to sketch the Bode plot. It makes it easier. Then we can simply add up terms. But if we're doing this in terms of finding the time constant form, do I give you time to work on that, or can you just tell me how to do that? What are we going to do to convert this pole zero form into time constant form? What's the main objective or point of time constant form? What are we trying to do? In this pole zero form, our poles and zeros are right there screaming at us in that constant term of the pole factors and the zero factors. What are we wanting to do to that constant term? I'm giving you hints if you hadn't noticed. What do you do to that constant term to put it into time constant form? You add a 1 to it? You add a time to it. Okay, well, how do we get the time of this? We factor that pole out and normalize that constant to 1 in each of these factors. And these are linear factors, and so it makes it even easier. Meaning, in this particular case, what we would have, we can't change the transfer function unless we're introducing a controller. But here, we have the 4, but if we factor out the 5, we now have the pole sitting underneath our S, and if you divided that 5 into 1, or the coefficient of that S is now 1/5, there's your time constant associated with that zero factor. It's multiplied by S, which is a frequency, something per time, and now you're scaling that. So if it's now radians per second, your S, what's scaling that or weighting that is now a time. And in this case, the time constant of that 0 is 1/5, or 0.2 seconds. We can do the same for the other two pole factors. If we factor out the first pole factor, we had a pole at minus 0.1. That's pretty close to the origin. What's its time constant? What's the time constant of that? It's now some tau times S. And the tau is 1 over 0.1, or 1 over 1 over 10, or it's 10 seconds. So you have a 10-second time constant associated with that pole at minus 0.1. And continuing or finishing, we can factor out the 20. And I'm writing it in this form so that I can explicitly see that pole, not so much the time, because I'm going to be plotting this on a frequency axis where I need the pole and zero locations. Meaning I need to know where the 5 is, where the 0.1 is, and where the 20 is on my Bode plot when I start sketching this. But in this point, or in this particular form, I can collect all of my constants and create a transfer function in time constant 4. 4 times 5 is 20, last time I checked. And 1 over 0.1, or 1 over 1/10, gives me now 10 S over 5 plus 1 over my two pole factors. This is now in time constant form. And I didn't modify G of S other than move things around. It's the same system. I now have my, in this case, the DC gain is that constant. It's sitting right there staring at me. If I set S equal to 0, that constant tells me exactly what my DC gain is. But what other key features of this system can we make or comment on when we're trying to sketch the Bode plot? What do we sort of need to be thinking about as we're drawing or anticipating the result of our Bode plot? What are some key features for this system? And really, in general, you might be trying to look at some of these ideas when you're starting to sketch this. And the first one I typically like to look for is, do I have anything happening at the origin? Do I have a pole or a zero, or poles or zeros at the origin? So that's my first sort of key feature here. Do I have any poles or zeros at the origin in this transfer function? Because if I do, those are always on. Those don't break. Those are always sloping in the magnitude plot, and they just give us a constant angle in the phase plot. And it's nice to sort of keep track of those. So I left enough space after my 1 to say there's no poles or zeros at the origin in this particular transfer function. Sorry about that if I messed you up. If you thought I was just tabbing over, I tabbed for a reason. Poles or zeros at the origin, you could say at the end not, exclamation point, if you don't say no, poles or zeros at the origin. I'll give you credit on the exam if that's the way you do it. Okay. Point 2. What was one part of a systems transfer function that we like to think about in the rule, I think it was rule 3 in the root locus? Do you remember rule 3? Not cheer 3. I may need to do some cheers today to wake up, but the asymptotes. So what did we focus on with asymptotes? The pole zero excess. That gave us our fundamental angle. What's the pole zero excess in this system? 1. And that now tells us at high frequencies what our phase is going to be. We have one more pole than we have zero, so at high frequencies this looks like a one-pole system. And what does one pole give you at high frequencies? Minus 90 degrees. So we know that's where we're headed in our phase plot. And that also tells us for high frequencies what our magnitude plot is doing. If we had just one pole, what would our magnitude plot be doing? That's maybe, it's sloping. And which way is it sloping, up or down, and how fast is it sloping if I have one pole? It's going down since it's a pole, and it's going down at 20 dB per decade. So you know when you finish, or when you're finishing your Bode plot, you better have at the end where you're doing the magnitude, it better be sloping at minus 20 dB per decade at high frequencies. Let me write that down somehow. So let me say here I have a pole zero excess of 1. Those are some of the key features. And what you just told me was based on that pole zero excess of 1, that as the frequency gets big, then we know that the magnitude in dB is sloping at minus 20 dB per decade, or minus 6 dB per octave. What's an octave? An octopus is 8, but that's sort of the key range. But octave in terms of frequency, if you went from middle C to the C higher, that's a factor of 2 in frequency. So an octave is saying a frequency change of 2 by a factor of 2. A decade is obviously a factor of 10. So if you're looking to find what's happening in a smaller frequency interval, maybe you just want to look at a factor of 2, then you're saying, oh, I need to be sloping at minus 6 dB per octave. if that's of interest. I shouldn't be saying of interest. You're going to just all check out and say, I'm not interested in that. So can I leave? I'm going to have to cut my paper. What else? Oh, we said at high frequencies, what's the phase doing? Where is it going? Or well, where will it be in your phase plot? That's going to be at minus 90 because your system at high frequencies is effectively looking like just a single pole because of your pole zero excess. This is now minus 90 degrees. In this particular system, since we do not have any pole or zero at the origin, then it's pretty nice in terms of where we start, where we pin our magnitude plot, because now we can immediately find the gain at low frequencies. If we have a pole or zero at the origin, it's sloping, and now you have to figure out, okay, where do I set my Bode plot, or where do I start my Bode plot? In this case, it's not that difficult, because now, what's our DC gain in this transfer function? So in terms of absolute value or number, it's 10, isn't it? Our DC gain is 10. If we wanted that in dB, it's 20 log of 10, or it's 20 dB. Let's now, whoops. Come back. Where am I? The magnitude now starts at a value of 20 log, and this is now base 10 of 10. That makes the log of 10 easy. That's just 1. So now we're starting our magnitude plot at 20 dB. And sometimes what I like to do is, besides cutting and pasting, is keep track of where I'm going to be switching my sketch. Where am I going to start bending or sloping or changing the slope? And that's all influenced by where my poles and zeros are, which I say, where are my breaks? So that's not the Thanksgiving break, but this is a break due to, so you can't start thinking about what you're doing on break until we finish today, right? So we'll talk about different kinds of breaks. These breaks are pole and zero breaks. And that tells us then what's going to happen to the magnitude at these particular points. For example, the pole, and I typically try to order these in advancing frequencies. Which pole or zero came first? It was the pole, and where was it? At what frequency? It was 0.1. And in terms of the magnitude, at that break, which direction is the magnitude going to, or what direction will the slope change? Up or down? Down. So I'm just going to give me an indicator. What happens next in terms of these frequency, these factors that I have in my transfer function? The constant is always there, and it doesn't change my slope. But the next one occurred at 5, and that was a 0. And what's the magnitude of the 0 factor do in terms of its slope? Since it's upstairs, it's going to convert the slope to a change of plus 20 dB per decade. And finally, then I have the pole, the last pole, and it was at 20, and that's going to cause my slope to go negative again. And if you're sketching this on the back of an envelope, which I'm assuming you might do on your break, you might want to keep track of this relationship between omega and log of omega, because we are plotting this relative to log of omega so that we can get more pieces or a longer frequency axis on the page. Last time we were told, or we remembered, the log of 2 to more digits, significant digits than I can remember, I just say 0.3. Okay, so it's about 30% of the distance between your two different decades of frequency. Then 3 is 0.48, but I typically will just round that to 0.5. If this is a hand sketch, I'm not going to get down to that resolution of 0.48. I probably won't even be accurate to 0.5. 4 is then 0.6, 5 is 0.7, and 8 is 0.9. So now you can just pull that out of your pocket. That can be your cheat sheet, and you can just have that omega, log of omega, carrying it around for years until you retire. And if somebody says, what's the log of 3? It's 0.48. I'm going to approximate that as 0.5. But you might eventually memorize those. Obviously, maybe I haven't. Okay, but we now have that to help us sketch our Bode plot. But maybe now you don't even need to sketch it. Maybe you already mentally know what's going to happen. If we are able to draw a straight line, and let's call this now our magnitude plot in dB. Where did we say we were starting? If we go back, where is 0 on this axis? It's way over there. It's beyond the Arizona-California border, I think, the way this class is oriented. Am I correct? So we never get there. We never get to 0 on a logarithmic horizontal line or horizontal axis. We never get to 0. We would just keep going 10 to the minus 2, 10 to the minus 3. But now that we have that, where are we going to start our magnitude at low frequencies? Where did we say our DC gain was? 10 in absolute, but in dB, 20 log of 10 is 20. So now we can start making, let's say this is now 20 dB. There's our magnitude. And where do we, how far do we go before we start changing from that flat magnitude? Well, we just have to go back to our notes. We go back and we say, oh, the magnitude is going to change at 0.1 the first time, and it's going to be going down with slope. And since these are linear factors, it's going down at 20 dB per decade. Which, if this is now 20, and I'm going down 20 dB per decade, I would just keep going in this direction. And if I could find this, and it would just keep going. But did something happen between 1 and 10? Yes, 5. So where is 5? Well, it's 70% of the distance between 1 and 10 on this logarithmic axis. So I'm just going to say it's about right there. That's why I tried to break my line. And now I can erase that, and I can come down with that same slope. But then once I hit 5, now I'm going down at 20 dB per decade. I now change my slope to introduce a plus 20 dB per decade. Now I'm flat again in terms of my magnitude. And how long am I flat? Until somebody tunes me? Never mind. A little musical reference there. But this is flat in magnitude. I now am going to be flat until 20. And where's 20? Between 10 and 100? It's between 10 and 100. But it's 30% of the way between 10 and 100. So let's now say it's right there. And I'm now flat until that point. And then I start decreasing at 20 dB per decade thereafter. And that was pretty quick. Just a few straight lines and some slope changes. And all we had to do was know that 5 was 0.7 roughly in logarithms and 2 was 0.3, and now we have that sketch. What's the phase curve look like? Are there questions on that? So if somebody gives you this magnitude curve and they say you have a minimum phase system, if I give you a minimum phase system, what does that tell you? If I give you that description in front of system, I say it's minimum phase, what does that tell you? It tells you the location of your poles and zeros are all in the left half plane. Now, if somebody says you have a minimum phase system and it produced this magnitude plot, you can now uniquely find the transfer function g of s from this. From this, you can see where its slope changes, and you can say, oh, I have a pole at 0.1, I have a 0 at 5, and I have a pole at 20. And then the only hard part is extracting the DC gain out of that. So now you say 20 dB is equal to 20 log of x, and solve for x, and that's your DC gain, and now you have your transfer function. Is that clear? So now we've done the inverse Bode plot and found a transfer function. You can do the same thing for a minimum phase system with the phase. But with a minimum phase system, all they have to give you is either the magnitude or the phase. They don't have to give you both. If you have a non-minimum phase, then you have to have both magnitude and phase to extract where is this zero or pole, because the magnitudes are the same, aren't they? For a right half plane zero or a left half plane zero if they're located at the same frequency. So you have to have both magnitude and phase plots if you have a non-minimum phase system. Now I shouldn't have scrolled down too far. Let me now try to draw a straight line. And the key word is try. And ideally you could line these up. I guess if you had your t-square, you could turn it around and have them now. What's our phase curve look like, or phase plot? At low frequencies, what's our phase at low frequencies? You can just put 0 in for S because I don't have any poles and zeros, and I can see that, oh, I just have 20, or I'm sorry, 10. What's the phase of 10? Since it's a positive number, it's 0 degrees. If it was negative, it would be minus 180. If you had a minus 10, you would say, oh, that introduced a complete different phase reversal. Now I'm starting at maybe minus 180. So we start at 0 degrees, and when do we start bending the phase curve? We have poles and zeros at 0.1, 5, and 20. Do we just start kinking our phase curve at those frequencies or breaking it? No. That's where we center the phase. So the phase curve is spread over 2 decades, and consequently we start a decade before and we end a decade after with respect to our slope changes. And the phase starts and stops. It's unlike the magnitude. The magnitude, you just have to turn it on and forget it. It's like an infomercial. You turn it on and forget it. Here you don't. With phase, you have to actually start it and stop the slope. In this case, we need to start the slope of that first pole at a decade before 0.1 or 0.01, and we start going in which direction? So in this case, we were here until 0.01, and then what happens? Actually, it gets a little bit challenging maybe to add and subtract or to keep track of all these bends and breaks on the phase. Sometimes it's not that easy to start at the left and just draw it to the right. So let's look at each individual piece. What's the individual piece do to this pole at point 1? Where does it eventually end up for high frequencies? What's its phase? I wanted to cover up the rest of that transfer function. I did it on my tablet. I hope you saw that on the screen. But if I cover that up, and now if I focus on that one factor of S over 0.1 plus 1, where does its phase begin? At low S, what's the phase of that factor? Now you're looking at j omega over 0.1 plus 1, and you set omega equal to 0. What's the angle of that term? 0, the angle of 1. Now if you let omega get really, really big, what's the angle? Now you have j big plus 1. It's now 90 degrees, and since it's in the denominator, it's minus 90. Meaning, we are approximating that to say that we will, let me say this is minus 90 degrees, and then this is plus 90. I'm centered over the actual pole location, but I now have to distribute that change over 2 decades. I know I start at 0, I end at minus 90, and so that's the piece that's contributed from that pole at point 1. What about the 0 at 5? Now I have to go to 70% of the distance between 10 or 1 and 10, but really I'm going to be starting at 0.5 and ending at 50. And it's going to now be, that doesn't look consistent, but just assume that that's the same, plus 90 in the positive direction as minus 90, and that's now the piece due to the 0 at 5. Did I locate it okay? And then I have my pole at 20, which is 30% between 10 and 100. So now I'm starting it at 2 and finishing it at 200. And now it does that. And now I have to add those up. Meaning, I look and see how many are active at any one time, and I adjust my slope accordingly. Initially, my slope, the only piece that's working is that first pole, and then I get to 0.5, and then it's going down and up at the same amount. So now I'm flat until here, and then what happens? Then my pole at 0.1 quits contributing phase change. It's going to give me minus 90. Now I have to go back up at plus 45 degrees per decade until I see more overlapping slopes. So now I go up until I hit 2, which is where the last pole starts kicking in, and then I go flat until where? Until I hit 50, and then I only have this guy left, and there's my phase curve. Wasn't that easy? All right. So now if I gave you that phase curve, you should be able to back out the transfer function. It's a little more difficult, but actually it gives you more times to check your work, because now you can say, I think its slope is changing at 0.01. Let me look. Oh yes, at 1 it's changing back. Anyway, questions on sketching Bode plots and inverse sketching? That's the system identification piece. What what we want to do now is look at stability margins. So now I'm giving you a different system, magnitude and phase. This is your quiz, and I now want you to find the gain margin and the phase margin associated with this particular system. Begin. I don't want to go into the vacation or the break this happy. So what do we need to do with respect to stability margins? What are we focusing on? What point or what complex number, and that you don't even have to put on your piece of paper in your pocket. What's the magic number that we've been concentrating on quite often in this class? That was a vague question. So if you're looking at the denominator of a classical system, it's 1 plus g of s. If you now solve that for g of s, what's g of s equal to? It's now equal to minus 1, isn't it? Minus 1 is that magic number. Minus 1 we can write as minus 1, or we can write it as 1 at an angle of minus 180. So we are interested in when or how much margin do we have relative to the magnitude and phase when they would simultaneously give us 1 at minus 180. So even on the final, you're going to have to answer something like this, I'm guessing. Hint, hint. So now, if you're looking for the stability margins of a Bode plot, and you have 1 at an angle of minus 180, the first thing you need to do is find when is my magnitude 1, or when does it cross through 1, and when does my phase cross through minus 180? Can you find those frequencies? Those are now your gain crossover frequency and your phase crossover frequency. So where on this magnitude plot does that plot cross through 1? And now you have to remember 1 in dB. So 20 log of 1, and this is log base 10 of 1. What's log base 10 of 1? Something in my eye. It's 0, right? Log of 1 is 0. 20 times 0 is 0. So now we're looking, what frequency does the magnitude plot cross through 0 dB? And you say, there it is, my gain crossover. And you could even tell me the value of that in radians per second on the final. You go, okay, give me some points, please. You're pleading, right? If it's multiple choice, those pleads will go unheard. No. So now we have omega sub g as 2. That's our gain crossover. Where's our phase crossover? It's when our phase curve crosses minus 180. Does it ever cross 180? Sometimes it will not. It may just approach asymptotically, which means that our gain margin would be infinite. We could just keep cranking up the gain and still be stable. And you saw that on Bode plot. I'm sorry, on root locus, right? When you had a two-pole system and your root locus was doing this, how much could you crank up the gain and still remain in the left half plane? You can crank as much as you want. You're staying in the left half plane. That's an infinite gain margin system. In this case, obviously it's not. Where is our phase crossover? So what's this line right there? This is logarithmic, so now that's about 30% of the way, right? I only have so many grid lines, and they occur at 10, 20, 30. So that's at 20. It's a little bit beyond 20, our phase crossover. Is that okay? So now our gain crossover is at 2 radians per second. And our phase crossover, let's just say that's at 22. I like 2s. 2s are wild today. Only today. They're on sale. Okay? So we have 3 2s. 2 and 22. To be 22. Okay, so now omega sub p and omega sub g, you've got those indicated. Now what do you do? Now you have to match them with the magic number of -1. You say, what would I have to change my phase? How much can I change my phase before it decreases to -180 when my magnitude is 1? That's my phase margin. How much can I change? So now I look at where I crossed the gain curve, which is, let's say, right here, and I say, oh, I can actually change my phase by that much before I simultaneously would have a gain of 1 and a phase of -180. This is now my phase margin. So you get the gain crossover frequency, that gives you your phase margin. The phase crossover gives you your gain margin. Is this making any sense? Again, all we're working on is this magic number of -1, 1 at 180. Now, can we increase our gain and still remain stable in this system? Is our magnitude below 1 or 0 dB when we have our phase crossover? In this case, we have our phase crossover here, and we go up and we say, oh, is that below 0 dB? It is, isn't it? So we do have, this is now our gain margin. And now maybe you struggle with this, but you have to eyeball it on the exam. You just have to sort of say, how much are these values? How much can you change your phase before you reach -180? Well, in this case, your phase margin can be reduced as much as, well, it's not quite 90 degrees because you're below -90. But now your phase margin, hopefully you can eyeball a little bit better than 90 and 89, but I would say that's more like 75 degrees. So you now have a phase margin of 75 degrees, which means that you can tolerate some delay in your system in practical terms. What about your gain margin? How much can you increase the gain before you go to hitting 0 dB when you have your phase crossover? Again, you just have to eyeball it. And this is actually a linear curve or distance, isn't it? So now we're about 60% of the way maybe between 0 and 50 or -50. So we could increase this. Oh, I'm really getting precise here, 28 dB. But on the exam, hopefully you can see that that's a little bit more than halfway, so you know it's bigger than 25. Maybe it's a little bit less than 40, so if you say something between 25 and 35, that's probably a valid answer on the exam. Is that clear? And that would be your gain margin. Questions on stability margins. If these are negative, your system's unstable. And what we will learn is if we want to make our phase margin bigger, then what could we do? Well, we could lower our magnitude curve to make it cross 0 dB sooner, and then we get more phase. Or we can start shaping the phase curve, and that's where this phase lead and phase lag description come into play. Phase lead increases our phase, and the more that we slide that magnitude curve to a lower frequency, the slower our system becomes. That 0 crossover frequency on our magnitude sort of is an indicator of how fast our system is responding or capable of responding. Meaning if we slide or lower our gain, if we just reduce the gain, that gain curve would go down and we would start crossing at a lower frequency. But that's, in effect, slowing down your system response. But it's improving your phase margin, which will help you with percent overshoot. It will make your percent overshoot better or effectively less. Wow, where in the world? Thought I had something here. System identification. What's this? This is now, can you tell me, maybe I shouldn't set these questions up this way. Can you tell me anything about G of S by looking at this magnitude and phase information, by looking at the Bode plot? What key features can you start to extract from these Bode plots, the magnitude and phase, about a G of S? And before we even start worrying about where the slopes are changing, can you give me some rough idea in terms of maybe looking at the phase curve? At high frequencies, what's happening? What's your phase at high frequencies? Minus 270. What does that tell you about your poles and zeros? How many more poles do you have? Each pole gives you minus 90. So now you have 3 more poles than zeros, ultimately. That's what the phase of minus 270 at high frequencies tells you. So now the G of J omega is going to minus 270 degrees for large omega. And that now says that whatever you end up with, you better end up with a transfer function that actually has a pole zero excess of 3. What about at low frequencies? What's your phase? Minus 90. It's not 0, is it? So if it's minus 90, what's that telling you? You have a pole at the origin. The phase of G of J omega is now minus 90 degrees for small omega. And that now says that we have a pole at the origin. So that now I could say, okay, I have G of S that's like this, and I know that I now have something like that, maybe. Or I need a pole zero excess of 3, so if I had 4 pole factors, I would need a 0 factor. Is that clear? That's what I've now determined from just looking at the phase curves extremes. Can I go back and find any of these frequencies? Do I ever seem to go up in slope in my magnitude? So I probably don't have any 0 factors, do I? And now I'm looking to see, is there a slope change anywhere? So I'm going along here, and then something sort of happened, didn't it? So where did those 2 slopes change? Well, in rough terms, they changed at 10, didn't they? So now I have a pole at 10. So I can now put that in here. I can say, oh, I have an S over 10 plus 1, and I'm putting it in time constant form. Do I have anything else changing? So I'm going along here. Oh, kind of changed again, didn't it? So now I go back here, and I say, where did that happen? Don't laugh at me. You're laughing with me. Okay, that's allowed. So where did those cross? And do you see how maybe uncomfortable this is making you feel? It's kind of loose and subjective. That's okay. Where did those two lines cross, roughly, if you could see through that blur or that blob? But it's somewhere in here, isn't it? Wow, I'm way off in terms of what I had before. But anyway, in this case, that would be, is that right? It was between 100 and 1,000. And now we would have to find K. How do we find K? We could now say, let's go back to a low frequency, maybe before any of our poles start breaking, before 10, and just find, maybe we could even find where it crossed 0 dB. And now the only thing working at that frequency is this guy. So at low frequencies, we could say, what's our G of J omega, or G of J omega in dB? And if it's at the crossover, it's 1, isn't it? But in this case, this goes away, and all I have is I have K over J, and if I found where that was at, that's at 2. And this is all the magnitude, so the magnitude of J is 1. So I now know that this is K over 2, and K over 2 is equal to 1. I have K. So now I know my K. K is 2. So now I have K, I have a pole at the origin, and I have two pole factors that I guessed their breaks at, and I could try to verify that with against the phase curve to maybe resolve that a little bit finer. And I would probably say that I messed up, because if I go back to the phase curve, where did my phase quit? It quit introducing phase at about 800, so my break is really a decade before that. It should have been like at 80. So my black lines are really messed up, aren't they? So I can change that real easily here by simply saying 80.0. But I hope you get the idea, and now what you need to be able to do is extract your G of S from this Bode plot information. And we'll pick up somewhere, probably with drawing or designing phase lag controllers next time.